And then, like I said, the Grignard reagent will react with all sorts of things. And one of the things that it will do is it can react with parts of your molecule you don't want it to react with. And so this is the first time that we're really talking about this, but we can actually protect parts of our molecule if we don't want them to react. And it's a little bit, uh, there's a lot of different ways we can do it. And actually, there's lots of publications, and there is actually a big, huge book called The Greens Protection. I don't remember if that's exactly the name, but it's a big, thick book, and you can look through and find, all right, does this look kind of like my reaction, my molecule? Can I use these kinds of things to protect my molecule? So here's an example. Let's say I wanted to do a Grignard where I wanted to use this Grignard to react with this ketone. But the, the problem is that Grignard I want to use has an alcohol in it, so it would actually react with itself. So instead of reacting at this position, which is right here, it would react with itself even faster before I could even put these things together. So that's a bad thing. So what I want to do is make sure that the way to think about it is I block it. It's kind of hidden. I'm putting a shield around it so it can't do any reactions I don't want it to do. And so how do we do this? We use what's called a protecting group. And there are different kinds of them, and I'm only going to give you an example. And there are others for other function group. It's not just alcohols. And so what you do is before you even start the reaction, you protect the group you don't want to react. So for instance, in this case, I want a Grignard right here. So I protect the alcohol, make my Grignard, do my reaction, and then I can remove the protecting group at the end. An example of some reagents that are often used are things like sulfur or silicon groups to replace the hydrogen on the oxygen. And this group, the OH is replaced with this silicon group, which we call TMS. So not quite the same as TMS that used for NMR, but same abbreviation. It's a silicon group with 3 methyls, whereas the one for NMR is actually 4 methyls. And you replace the hydrogen, and this makes it unreactive to strong bases and nucleophiles. But it is reactive to acids. So that's actually the key. Can I do this reaction? The Grignard is a strong base, it's a strong nucleophile, so nothing will happen to it. But when I'm done, I can remove it in an acid or some other reagent that can break it apart. So I can use a strong acid, or there's another compound called TBAF. You don't need to know the structure of that and use that to separate them to replace it. So after I do this reaction, I can use TBAF or a strong group to return it back to the alcohol. All right, the last few things in this chapter is that we can use oxidation reactions to essentially reverse the reduction reactions that we saw before. So it's basically if you added 2 hydrogens, you just remove the 2 hydrogens. And then there's some things that we have to keep in mind. So if you have a primary alcohol, remember we can make an aldehyde and we can reduce it to a primary alcohol. Well, oxidation would just be the opposite. So anything that we talked about with the reducing agents, we can go backwards. There's only a few things that we have to think about in these cases that I'm going to point out. One thing is that there's lots of different oxidizing agents, and it depends on what you need. So for instance, an example of an oxidizing agent that you know from Gen Chem, an organic one, is potassium permanganate. Another one is sodium dichromate, and there's some other ones, and it usually has an acid in it. But one problem that so we can represent those generically with an O in the square brackets. One of the problems is with the aldehyde, aldehydes are so reactive that they can keep being oxidized and they will go to a carboxylic acid. So that's something to keep in mind. Now, there are some milder oxidizing agents that you can use. An example of one is a reagent called PCC. PCC is so mild that it will go from a primary alcohol to an aldehyde and stop. So that's something to note. The second thing I want you to note is that a secondary alcohol, once you oxidize it, you have a ketone, but there's no more hydrogens to remove, so there is nothing you can do further. And lastly, a tertiary alcohol has no hydrogens on the alpha position to remove, so there is no oxidation that's going to happen in the same way that we've seen before. However, with certain kind of groups that have no hydrogens on it, like a phenol, there's some rearrangements that can happen, these redox reactions that can happen, which are very important actually for biochemical purposes. So phenols, even though they have no alpha hydrogen to remove, can undergo oxidation. But what it does is because of resonance, we can rearrange the structure and we get these kinds of structures. I don't need you to know the mechanisms for the reduction, for the oxidation reactions, especially for this one, but I want you to note that you're going to go from a phenol and then they go through a variety of steps until they get to something that looks like this. And depending on what else is on the ring, you can get different things. So for instance, this particular compound is used for electron transfer in biochemical processes, has some methyl groups and methoxy groups and things like that on them. So let's talk about our last couple of reactions related to alcohols before we move into ethers and thiols. A lot of reactions that we do with thiols are pretty much similar to those that we do with alcohols. And things that we see in previous chapters are going to kind of come back there. So we're going to cover the most important parts of those later, but let's kind of finish up our alcohols. So in this reaction, I have a mechanism to help you to explain what's going on. I'm not going to ask you to draw the mechanism for a test or anything. You should kind of have a gist of it or be able to understand what's going on in it. But for test purposes, this is not one that I would suggest that you spend too much time trying to practice. But in terms of our mechanism here, you'll see that the alcohol, being our nucleophile, is going to attack electrophilic sulfur right here. So it's partially positive. We have the chlorines and the oxygen that can pull electron density to it. It bumps up a lone pair to the oxygen. And so we get this kind of complex with the forming kind of like a hydronium. And the reason that we're doing this in this reaction is that we are, in the hopes, if you look over here, we're trying to make a primary alcohol. So we essentially want to do kind of like a SN2 style reaction. The problem that we don't want to have is things like rearrangement. We also don't want to have any problems with any eliminations or anything like that. So this is actually one of the most effective reactions that I've actually done where you use thionyl chloride. And thionyl chloride, it is actually kind of corrosive, but there's some substitutes that people have used out there. So there are other kinds of compounds, but for our class, we're going to focus on thionyl chloride. But there are, so there's something called oxyl chloride. That's actually a greener version. That's actually something that I'm actually going to focus more on in my research rather than using thionyl chloride in the future. And we can do this reaction to make this product, this SN2 product. But the other problem that we've learned is that, remember, OHs are bad leaving groups, so you could protonate, but this is not, In theory, I could just use HCl to do this, but it actually isn't really effective. It doesn't work terribly well. This works really well because I'm creating, by making this thing, I've actually started to become in the process of creating a good leaving group. So when the oxygen collapses back down, it kicks out a chlorine. That's very important because we're going to need a chlorine to then attack and kick out my leaving group. So once I get to this point, actually, you will see here that we have something called pyridine. You've seen this before. Pyridine is just being used as a base to basically sop up these extra hydrogens. And then your chlorine comes in an SN2. So this is really just an acid base and an SN2 reaction anyway, and the chlorine comes in. And you get your alcohol. So since it's an SN2, this is only going to work with methyl, primary, secondary. It will also work with benzylic and allylic, but it will not work with tertiary. And it's very slow even with the secondary. But for the purposes of our class, I want you to solely focus on just what the products are. So thionyl chloride in the presence of, this is actually a very small amount of pyridine, and we pretty much get just the chlorine. It's almost 100% usually. The great thing is sulfur dioxide is a gas and it just not evaporates, but you can get that out. And chlorine is not usually, that excess chlorine is usually not going to do anything in the flask. If anything, you just wash it away with water. Now, another way that we could do these kinds of reactions, it's not as effective, but sometimes people use zinc chloride as a Lewis acid instead of doing like a protonation, and then follow that up with your chlorine. And so I'm just going to shortcut, not shortcut, but show you kind of step by step. So first you have this zinc chloride intermediate, making the OH a good leaving group, and then the chloride ion from the HCl comes in and kicks this out. So that's another version of reaction that people sometimes do, but this is still the best. So you can use this reaction with the zinc chloride. It actually is called a Lucas reagent. It's a test that people often use to test whether or not you have alcohols, primary or secondary alcohols. So what if you wanted a bromine instead? There is a version of this that you can use bromine. It uses phosphorus tribromide, and phosphorus tribromide will do the same thing, will form this complex that makes a great leaving group, and then your bromine can come in and kick that leaving group out. And then you get your alkyl halide out, and you get a salt that you just wash away with water. But again, I don't want you to focus and fixate on the mechanism. I really want you to focus on what the products are. Again, this is an SN2, so again, it will work with methyl, primary, slow with secondary, but it can work. It definitely works really well with allylic and benzylic.